Hello everyone, my name is Margaret and I'm in Mr. Ferrar's third period AP Calc BC class, and today I'm going to be going over question 3 from the 2009 AP Calculus BC FRQ problems. This is a calculator OK problem, so for some of these parts I'm going to be utilizing my calculator to show you how to work through the problem more easily. And since this is a word problem, I'm going to go ahead and read the section describing the figure. And it states that a diver leaps from the edge of the diving platform into a pool below. The figure above, which in this case is to the side, shows the initial position of the diver and her position at a later time. At time t seconds after she leaps, the horizontal distance from the front edge of the platform to the diver's shoulders is given by x of t, and the vertical distance from the water surface to her shoulders is given by y of t, where x of t and y of t are measured in meters. So keep that in mind later on when your answer is asked for units. And then suppose that the diver's shoulders are 11.4 meters above the water when she makes her leap, and that's important because that gives us this length and is useful as the initial position. And then it gives us that dx dt is equal to 0.8 and dy dt is equal to 3.6 minus 9.8 t, where t is in between 0 and a is the time that the diver's shoulders enter the water. So for part A of this problem, it asks us to find the maximum vertical distance from the water surface to the diver's shoulders, and as you can tell by the figure, that's going to be this whole length. But the first thing that we need to do is figure out at what time t the diver will be at this point. And so to do that, we need to figure out the tangent to this point, and so that's just going to be where dy dt is equal to 0. And since we're given dy dt, we're just going to set that equal to 0 and solve for t. And that'll give us that point at which the horizontal tangent would be equal to 0. And so, as you can see here, I manipulated this equation and moved 3.6 to this side and then divided both sides by negative 9.8 to get t is equal to 0.36735. And so for the purpose of the next section, we're going to switch variables and let t equal b. So now, solving for the whole length, we have y of b is equal to that initial position plus the integral from 0 to b of dy dt dt. And so if we plug in dy dt and b, we get this equation. And so to solve for this part, we're going to use our calculator. So what you're going to do is you're going to press math and then go to 9, and that'll give you that integral with a bunch of blanks, and we're just going to fill that in. So the lower limit is 0, upper limit is 0.36735, and then inside the parentheses we're going to put 3.6 minus 9.8, and then here the variable will be x, and make sure to match that variable here. Click enter, and that gives us 0.661224, etc., which I have written here. And then all you have to do is add those together, and you get 12.061 meters. And then another way that you can do this is instead of having to go through the whole integral process, you can just integrate this at the beginning. So integrate that initial dy dt right here, and that'll give you 3.6t minus 4.9t squared. So that and the initial position of 11.4 will give you y of t as well. And so for this, you just plug in the t value that we saw for up here, so b. So y of b is equal to 12.0.61 meters again. So that's just two different ways to solve for that. And then the breakdown of points here, it gives you 1 point to consider dy dt is equal to 0, so that point right here. Another point for the integral or y of t, so those two different ways that I showed you, and then 1 point for the answer. Okay, and so for the next question, we have find A, the time that the diver's shoulders enter the water. So in order to do that, we're going to utilize that same equation that we just made for y of t, but use it in terms of y of a. So y of a is equal to 11.4 plus the integral from 0 to a dy dt dt, and then again change it into that form that we just had. And then for this, we're just going to solve it and make it equal to 0, and we're going to use our calculators for that again, because we know that when the shoulders enter the water is going to be when y of a is equal to 0. So for this, we're going to go to y equals, and we're going to plug in 11.4 plus 3.6 x minus 4.9 x squared. And we're going to graph that. Okay, we have that. So second calc, 0, enter for that lower bound, and then enter for the upper bound. And we get that x is equal to 1.936255. And so we're just going to cut that off at 3, and that's at 1.936 seconds. And that's going to be useful for other problems. So here, the breakdown of points is 1 point for the equation and then 1 point for the answer. And now for part C, it says find the total distance traveled by the diver's shoulders from the time she leaps from the platform until the time her shoulders enter the water. So for total distance, we're going to use the distance equation, which is d is equal to the integral from 0 and then to a of the square root of dx dt squared plus dy dt squared dt. And so again, I just plugged in those equations and then the upper limit. And so again, we're going to use our calculator. So go to math again, go to 9 for the integral. Lower limit is 0, upper limit 1.936. You could leave it at that, but I like to go several more decimal places just to get a more exact answer. And then you're going to go square root, and then dx is 0.8, and then squared, plus 3.6 minus 9.8 x squared, and then dx. Enter. And that's going to give you 12.94621. And then if you just leave it at 3 decimal places, that gives you 12.946 meters. And so here, breakdown is the integral, 1 point, and 1 point for the answer. Last part, it says find the angle theta being in between 0 and pi over 2 between the path of the diver and the water at the instant the diver's shoulders enter the water. So if you look at this figure, you can create a triangle shown right here, where this is the path that the diver is taking, and then this is the water. So this would be the angle that we're searching for. And we have dy dt and dx dt. So we need to find a trig function that utilizes both the opposite and the adjacent. And that, of course, is tangent. So first we have to find dy dx at time equals a, and we already saw for a. So we just plug that in to, this is dy, and then this is dx, and that gives us negative 19.21913. And then, so we're just going to plug that into the inverse tangent to solve for theta. And we can drop this negative because it's simply a ratio between, because this is negative and this is positive, but in reality it doesn't really matter. So then we plug in the positive version of that, and we get this number, which we can just leave as 1.519. And we don't need units for this because it is an angle. So I hope this was helpful. If not, I'm going to have an attachment in the description box of a problem that I created myself, and hopefully that will help you as well. And then one last thing, don't forget that the breakdown of points is 1 point for dy dx at time A and another point for the answer. Hope you enjoyed my project. Thank you for watching.